let's take a look at an application of binomial coefficients, another math problem. So we were given some string, and we want to compute how many different strings we could make with the same characters. So here we have AA, BA, C. So 3 A's, a B, and a C, and we want to figure out how many different strings we could make. And so how can we do this? Well, we need to pick 3 of the places to be A's. So there's 5, choose 3, or 10 ways to do that. And then the remaining place is we need to pick whether it's B, C, or C. So there's 2 ways to do that. And that's why there's 20 strings. This is a simple combinatorics problem. And yeah, let's get into coding, and we'll explain how to do it as we're going. But the major difficulty is going to be computing binomial coefficients. So the first thing we need to do is count how many copies of each character we have, right? That's all that we care about. It doesn't matter where the A's are in the original string. All we care about is how many A's we have, and B's and C's in all the way up to Z. So there's 26. So this is going to be the counts of each letter. There's 26 letters. So for the 0. So this gives us, right, so in ASCII, which is the way that characters are actually stored as numbers, the lowercase letters are all consecutive, so the uppercase letters, so the digits, it's very convenient. So we can do character subtraction to give us an index from 0 to 25 that represents the letter, right? So lowercase a is 0, because a minus a is 0. Lowercase b is 1, all the way up to lowercase c is 25. So this conveniently gives us an array index to this count vector. So now that we have all the counts, we can compute the answer. So as I sort of alluded to, the way that you can compute the answer is first you place the A's, right, and there's C, let's just say n is a step size. Let's call it B, actually, here I use C to count. Right, so this is how many ways there are to place the A's, and then you need to place the B's. How many ways are there to place the B's? Well, you can't use the places where you place the A's, so there's n minus CA places left, and you choose B of them, or CB of them, to place the B's in. And so on, right? Now you can place the C's, you can't place them anywhere you place A's or B's, and you need to place CC of them. And so the final answer is just going to be the product of all this, because there's this many ways to place the A's, and there's this many ways to place the B's, and they're totally independent. Any way of placing the A's can be paired up with any way of placing the B's. And so you can multiply them, because you can pair them up any way you want. That might sound confusing, because you can't, obviously they do interact. You can't place an A and a B in the same spot. But the point is that if you think of placing the B's not in specific spots, but within the spots that are now open, right? So instead of placing the B's in the 3rd and 4th positions, you're saying I'm going to place the B's in the 3rd position that's still empty and the 4th position that's still empty. Then they don't interact with the A's, right? Anyway, because the point is that any way that you place the A's, there's going to be this many empty spots left. And so if you just place the B's within those empty spots, then you don't need to care what happened to the A's. And that's why they're independent. So similarly, place the C's, place the D's, all the way down to the Z's. And of course, so multiplication, we need to do modular multiplication. So otherwise we'll get overflow. And we saw in the binomial coefficients video how to calculate binomial coefficients, which was fn times fi k times fi n minus k. N minus ci. And now we need to subtract off the number of empty spots. I'll just call this empty. Size. So this is the binomial coefficient, and then we can multiply it into the answer, and eventually just print out the answer. So now we can decompute the s and the fi's, just like we did in the binomial coefficient problem. We'll just do that again. And it can be up to 10 to the 6th, right? We could just have it all a's, so let's just do that. Right, so again, 1 over n factorial times n is 1 over n minus 1 factorial. So to get 1 over I factorial, we start with 1 over I plus 1 factorial, and then we multiply by I minus 1. We need stuff at the top. So we always need adding, we need vector here for f and fi. We always need using x squared. We always need LL. And then we need the modular stuff. So we actually add times y. So we get this add. Then we use my notation of squaring. So e to the e is b squared to the e over 2. And otherwise, we just take off the power of b. And we said that the inverse of x is x to the mod minus 2 because of this theorem that x to the mod minus 1 is always 1. And that should be it, actually. All right, so we got it. Yeah, so said it's an application of binomial coefficients, right? Because we need to choose where to put the a's, choose where to put the b's, choose where to put the c's, and so on. And the number of ways to choose to do something is binomial coefficients. So I kind of went pretty fast over the actual binomial coefficient stuff. So if you didn't quite follow that, go back to the binomial coefficient video where I explain it a little slower. But the key idea here is how to actually use them, right, which is successfully placing each different character within the empty spots. Right, so we're choosing CI from empty, which is f of empty times 1 over f of ci times 1 over f of md minus ci. Yeah, so that's the problem.